Hello friends, welcome to my channel. So in this video I'm going to explain you some of that is physics, 12th physics, nuclear physics chapter, the most important things for your any competitive exams. So let us see what are the things we are going to read. So first we are going to learn about neutron, nucleus, mass effect, binding energy, binary energy curve, nuclear reaction, nuclear fission, fission and nuclear fission and fusion, nuclear reactor, nuclear bomb, radioactivity, radioactive disintegration, radioactive series, successive disintegration, and radioactive equilibrium. So these are the 12 topics that we are going to learn in this nuclear physics chapter. Okay, so first, so according to Rutherford's scattering experiment that you have learned from your 10th, and according to his experiments, he established that the mass of atom is concentrated with small positive charged region at the center, which is called nucleus. So mass of the atom, it has a small positive charge that is called as nucleus, as you all know. And also nuclei is there, that is made up of protons and neutrons. Sorry, the number of protons in a nucleus is called as the proton number or atomic number, and is represented by a symbol that is Z. The number of neutrons is called as neutron number, and it is represented by N. So for calculating the total number of protons and neutrons in nucleus, the formula is for nucleus, or for mass number also we say, for mass number the formula is A is equal to Z plus N. So neutrons and protons, when we describe collectively, they are called as nucleons. Neutrons and protons, when we describe them collectively, when we explain, it is called as nucleons. So nucleus contains two positive of particle, that is neutrons and protons, and nuclides, it is represented with this formula where X denotes the chemical symbol of that element. Okay, this formula is also important. Now this was the basic. Now first is neutron, let us learn. So neutron, it is a fundamental particle which is essential, and it is constituent of all nuclei except that of hydrogen atom. Okay, so neutron, it is fundamental particle for all essential elements except hydrogen atom. For all elements, neutron, it is a fundamental most important particle. It was discovered by a scientist, that is Chadwick. The charge of neutron, so the neutron, it is neutral because it has both proton and neutron. So proton and neutron both, it has make nucleus or neutron, it is neutral. Sorry, I said by mistake nucleus. So neutron, its charge is neutral. Okay, and the formula or the mass of neutron, that is 1.6750 into 10 to the power minus 27 kg, and the spin angular momentum is 1 by 2 into h by 2 pi into j minus s. Magnetic momentum is 9.57 to 10 to the power minus 27 j, and some other information is given. I think this is not important. So this mass number, spin angular momentum, mass of neutron, magnetic moment, these are the important things they may ask. Meaning that most of the other things, it is okay, but it is not that much important, they may not ask you. And in neutron, thermal neutron, that is the fastest neutron, can be converted into slow neutron by certain material that is called moderator. So the moderator which converts the fastest neutron, the neutron that is the fastest, that neutron can be converted into slow neutron. The moderators like paraffin wax, heavy water, graphite. When fast moving neutrons pass through a moderator, they collide with the molecules of the moderator. So when the fast neutron, it collides with the neutron molecules, it collides with this moderator. As a result, the energy of the moving neutron, so the neutrons that will be moving, when it collide with this moderator, um, its speed becomes slow. Means the energy of the moving neutron, energy will be get decreased. while that the molecules of the moderator increases. So the molecules of the moderator will get more molecules, and the speed of the neutrons will also decrease, and energy of the moving speed of neutron also decrease. After sometimes both attain same energy. After some time both will get same energy, it will get neutral. The neutrons are then in thermal equilibrium with the molecules of the moderator and called as thermal neutrons. So the neutrons, it will be become thermal equilibrium, means after that it will become thermal equilibrium because it is neutral, energy is same, and it will get convert with the molecule of the moderator. It will join with the molecules that are there with the moderator. It will join, the neutrons will join, then it will become thermal neutrons. Okay, energy, you means the thing you have to note is energy of thermal neutron is about 0.025 ev and speed is about 2.2 kilometer per second. Okay, this was about the neutron. Now the next topic is nucleus. Okay, so there are many types of nucleus. So first, nuclei, many types of nuclei, also we can say nucleus. The nuclei has been classified on the basis of the number of protons, or we can say it as atomic number, or the total number of neutrons, or nucleons, that is called as mass number. Like first is isotopes. The atoms of elements having same atomic number but different mass number, we call it as isotopes. So isotopes you all will know, means you have learnt it in your 10th also. And isobars, nucleons having same mass number but different atomic number, opposite of isotopes. Okay, also we can say that it is the opposite of isotopes. Isotopes is the, it is having same atomic number but different mass number. In isobar it is opposite, means same mass number, different atomic number. Okay, examples, remember some of the examples like H1, H2, some O2, so like this, remember example. The third is isotones. The nuclei having equal number of neutrons are called as isotones. If nuclei has equal number of neutrons, then we call it as isotones. Like example also you can take here, many examples they are given. CNO, oxygen, okay, helium, many examples they are given. Fourth is mirror nuclei. Here nuclei having the same mass number A but with proton number Z and neutron number A minus Z interchange, or whose atomic number differ by 1. So if the atomic number it is differed by 1, then we call it as mirror nuclei. Okay, I think you understand, means nuclei having the same mass number, nuclei have same mass number, but when it combines with proton number and neutron will become A minus Z, means mass number minus proton number. Or we can also say it as whose mass number, means whose atomic number, it will vary by 1, it will vary by 1. Okay, I think you understand. Now size of nucleus. In first we learned different types of nucleus, that is nuclei, that, but now it is, we learned 4 types of nuclei, right? After that, the next thing in that nucleus we are learning is size of the nucleus, means nuclear radius. First is, that is, it is the experimental result which indicates that the nuclear radius is proportional. Nuclear radius, it is proportional to a to the power 1 by 3, where a is the mass of the nucleus. Nucleus radiation is proportional to a to the power 1 by 3. Okay, experiment they have done, where result they have got is the nuclear radius, it is proportional to a to the power 1 by 3, where a is the mass number of nucleus. A is the mass number of that nucleus. Next, means heavy example, means note also, that is heavier nuclei or bigger in size than lighter nuclei. So heavier nuclei, it has bigger in size than lighter nuclei. Okay, now is nuclear volume. Okay, the volume of nucleus is given by, so volume of nucleus you can take it by the formula, that is V is equal to 4 by 3 pi r cube is equal to 4 by 3 pi r O3a, means this is formula. Okay, mainly you can take it as V is equal to 4 by 3 pi r cube, it is better. Next is nuclear density. Here, nuclear density, as you all know, in 10th only you have learned, that is mass per unit volume of nucleus. What is the mass per unit volume of the nucleus is called as nuclear density. Nuclear density is equal to mass of the nucleus by volume of the nucleus. That is the formula, that is equal to m by a by volume of nucleus. That is the formula we got, that is 4 by 3 pi into ROA to the power 1 by 3 into 1 by 3 whole cube, right? Here this formula, total formula volume we are taking, where here m is the average of mass of nucleon, and ma, it is the mass of nucleus. Okay, here in this formula, ma, mass of nucleus, that we got m is the average mass of nucleon, and ma is the mass of nucleus. Okay, next is nuclear force. Nuclear force, forces that keep the nucleon bound in the nucleus. Forces that keep that nucleus bound in the, sorry, one minute. Forces that keep nucleon bound in the nucleus. Forces that make nucleon stay inside the nucleus are called as nuclear forces. So nuclear force are, say, some of the information about nuclear force is, it is a short range force. They does not exist at large distance, that is it is greater than 10 or 15 meters. So that's all. Nuclear force are strongest force in nature. Nuclear force after gravitational force and two other forces, the most important force is nuclear force in the nature. Strongest force, among strongest force, the most strongest force, that is gravitational force, and two other forces are there. And after that, the most strongest force is, the fourth strongest force is nuclear force. Okay, these forces are charge independent. They are attractive force. They cause stability of the nucleus. Nuclear force or non-central force. Nuclear force, it is a non-central force. So those are some of the information here they have given. I think it is not important, but let me just say it. So according to scientist Yukawa, the nuclear force between two nucleons is the result of the exchange of the particles. So according to the scientist Yukawa, the nuclear force that is between two nucleon, it is the result of the exchange of particles. It is the result that the particles are exchanged. Pi is the mesons are of three types: positive, negative, neutral. Positive, negative, neutral. The neutral, they also said the same. Next is dog bone analogy. That is, the above interaction can be explained with the dog bone analogy, according to which we consider the two interacting nucleons to be two dogs. So we are taking two nucleons as two dogs that are having common bone. Means they are having common bone, only one bone. How for eating one bone, both dogs will fight like that. Each one of these dog wants to take that bone. Means each one of the nucleon want to take that energy, or want to attract that particles that are near them. They seems to be bound to each other, strong attracting towards themselves, and the meson also plays the same role for the common bone in which two nucleons. So in similarly here, meson they have given, that is positive, negative, and neutral. These also play a most important role in this attracting the particles for the nucleons. Atomic mass unit, that is AMU. Okay, the unit in which atomic and nuclear mass are measured. So it is the unit in which atomic and nuclear mass can be measured. Atomic and nuclear mass is measured. This unit is called as AMU, atomic mass unit. Okay, indeed AMU or 1U, that is equal to 1 by 12th of mass of 6C12 carbon 12, that is equal to atomic mass value, it is 1.66 into 10 to the power minus 27 kg will get. Like this, mass of electron is equal to 9.1 into 10 to the power minus 31 kg, that is will be 0.000548 AMU atomic mass unit. Similarly, proton will be 1.6726 into 10 to the power minus 27 kg, that if we convert it, it will become 1.007276 AMU. Neutron also you can see. Okay. Next is mass energy equivalent. So according to Einstein, mass and energy are interconvertible. So according to Einstein, mass and energy are interconvertible. So the Einstein's mass energy relation is given as E is equal to mc square. So this is the most important formula that you may have heard about this formula. According to the means you may have heard this Einstein's mass energy formula, where mass is equal to 1 AMU. Let us take mass is equal to 1 AMU. C is equal to 3 into 10 to the power 8 meter per second. E is the electron is 931 MeV. So 1 AMU is equal to 931 MeV, or 1 AMU or 1 U. So therefore it is equal to 931 MeV is the answer we get. Next is pair protection and pair annihilation. So when an energetic where a photon falls on heavy substance, it is absorbed by some nucleus of that substance. So when a high energetic wire it falls, wire a photon, it falls on heavy substance, they absorb some of the nucleus of that substance, and electrons and a positron are produced. So some electrons and some substance are absorbed by that heavy substance, and it produces some of the positron. This phenomena is called as pair protection, and may be represented by the following equation, that is rest mass energy of each of the positron and electron is E naught is equal to m naught c, that is equal to formula. Okay, this is 0.51 MeV is the value we will get. So this was some information, a small information about pair protection. Okay. Now the converse phenomena pair annihilation is also possible when an means we learned about pair protection, right? In pair annihilation, whenever an electron and a positron come very close, so electron and positron when it come close to each other, they annihilate each other by combining together. So they produce some energy by combining together, and 2y photon means energy it is produced. When combined, they both combine, they produce some of the energy. The energy that is produced by them when means electron and photon, when they both combine, the energy is produced. The energy that is produced by them, it is called as the pair annihilation, and it is represented by this equation. So this equation we write 1 BO, that is positron, plus minus 1 BO, that is electron, that is equal to HV, that is y photon that is produced, plus 2 HV5 proton is produced. Next is nuclear stability. That is, among about 1500 known nuclei, less than 260 nucleus are stable. So less than 260 nucleus are stable among 1500 nuclides. The other nuclei that are is 1300 1240 nuclides, they are unstable, means that unstable, that decay to form other nuclei. They may form other nuclei as they are unstable. They will try to form some other nuclides by emptying or by wave particle process or by YEM waves, electromagnetic wave process. This process by which the decayed or unstable neutron tries to convert into it decays and it forms some other nuclides. The unstable nuclide, it gets decay, it means it dies, and it tries to form some other things like emitting beam particles or electromagnetic waves. This produces some of the radioactivities. It means some of the energies it produces. Thus, thus the stability of the nuclei, it is determined. The stability of nuclei we can say on many factors, like how is neutron proton ratio, how much of the neutron and protons are there in that reaction in that nucleus. Like the chemical properties of an atom are governed entirely by the number of protons in that nucleus. How much is the proton in that nucleus, we can say yes whether the proton is stable or not. The stability of an atom also depends on number of protons and number of neutrons for a lighter nucleus. So how much number of proton and how much number of neutron is there in that nuclei or nucleus? It tells us about the neutron-proton ratio, means whether the nucleus is stable or not. And the formula is approximately equal, that is n by z is equal to 1 is the formula. Heavy nuclei are stable. So heavy nuclei are stable only when they have more number of neutrons than protons. So if heavy nuclei is there, it will be called as stable if it has more number of neutrons when compared to protons. Thus heavy nuclei, it is neutron rich. For heavy nuclei, more is the number of protons in the nucleus greater than the electrons repulsive force between them. Therefore, more neutrons are added to provide the strong attractive force. So, if it has more protons, heavy nuclei, it is electrically repulsive force it will make. So, for if we add neutron to that, it will become electrically attractive force. Means it will attract the elements that are near the things, and it will make the nuclei as stable. Okay, I think you understand. The figure they are given here, it shows n versus z for the stable nuclei, that is number of neutron by proton number. So A is equal to 40. So this is a small example. I think it is not necessary for you. So a nuclei above the line of stability having excess neutron decay through B emission, that is neutron change into proton, thus increasing atomic number Z and decreasing neutron number N in B emission. N by Z ratio is decreases. N by Z ratio, neutron by proton ratio, it will decreases. Okay. After that is even or odd number of Z or N. So the stability of nuclide is also determined by the consideration whether the nuclei it contains even or odd number of protons and neutrons. If it is found that even nucleus is there, then it is more stable, because 60% of stable nuclides have even Z and even N. If we found that even odd nucleus is there, means even number of proton and even number of neutron are there, or odd even neutron are there, then we can say it as it is lesser stable, while odd nucleus is found to be less stable. So if odd nucleus is there, then the neutron it will be less stable. So that's why we say it as the neutron will be less stable if it has odd nucleus. If it has even nucleus, then we can say it as the neutron is more stable. Okay, after this, the last, that is binding energy per nucleon. In this binding energy per nucleon, the stability of a nucleus is determined by the value of its binary energy per nucleon. Means in general, higher the value of binding energy per nucleon, more stable the nucleus is. Means if you say, if the binding energy of the nucleon is more, then we can say it as nucleus is stable. Means binding energy per nucleon, what is it? It is the stability of nucleus. It tells us how much stable the nucleus is by telling us the value of binding energy. Binding energy of the nucleon means binding energy. Now you may not understand. Next topic, that is mass defect and binding energy. Here you will understand what is binding energy. Okay. Now it is binding energy per neutron. It tells us whether the nucleus is stable or not. If higher value of binding energy is there, then we can say it as nucleus is stable. Only this much you have to understand. Okay, this is the thing we learned in this topic, that is nucleus, stability of the nucleus. We learned different types of stability of nucleus. Now, mass defect and binding energy. Let us come to this topic. Next, mass defect and binding energy. In this topic, we first let us see what is mass defect. The symbol denoted is delta M. It is found that the mass of nucleus is always less than the sum of the mass of its constant nucleon in free state. Okay, means that is, we find that the mass of nucleus, it would be less than the sum of the mass of the nucleons in free state. So when the nucleons it is in free state, and the nucleus that is the mass of the nucleus, it will get, it will be lesser when we compare to the mass of the nucleons that are very free state, it is moving. So they are saying that mass of the nucleons that are free, when we compare to the, when we compare that mass of nucleons that are in free state with the mass of nucleus, the mass of nucleons that are in free state, it has more values, means it has more mass. Okay, that is delta m is equal to sum of mass of nucleons minus mass of nucleus. So this is the most important formula also. The questions may be asked depending on the on this formula. So please remember this formula. Zmp plus a minus zmn minus m is or is equal to zmp plus zme plus a minus zmz minus m mass. Any formula you may learn. Here mp that they have given, that is mass of proton, mn mass of neutron, me mass of electron, mass m is the mass of nucleus, z is atomic number, a is mass number, m dash is mass of atom as whole. Totally, what is the mass of atom? Okay, so I think you understand mass defect. So next, before going to binding energy, some small topics are there. First, finish that, as binding energy is more huge topic. It is a little bit big topic. So before going that, let us finish this. The next topic, that is, it is packing fraction. It is easy, that is mass defect per nucleon is called as packing fraction. There are mass defect that is per neutron, it is called as the packing fraction. Simple definition. Packing fraction formula is delta m by a, that is equal to m minus a by a, where m is the mass of nucleus, a is the mass of number. That's it. Okay, simple. Next, now the big topic, binding energy. Binding energy means the neutrons and protons in a stable nucleus are holding together by nuclear force, and energy is needed to pull them infinitely apart. Means neutron and proton in a stable nucleus. In a nucleus, both neutron and proton is a nucleus. Stable nucleus is there. Imagine it has nucleus. It has both proton and neutron, as you all know. They both hold together. They both are hold together by a force that is called as nuclear force, and energy is needed to pull them infinitely apart. So to pull them to other places, the energy is needed, or the same energy is released during the formation of nucleus. During formation of that nucleus, how nucleus is formed? By combining proton and neutron. So by for combining that proton and neutron, energy is needed. Formation of proton and neutron, that energy is also called as binding energy, that binds the proton and neutron and forms a nucleus also, we can say. And this energy is called as the binding energy of the nucleus, or we can say it as the binding energy of nucleus may be defined as energy equivalent to mass defect of the nucleus. Mass defect means if delta m, it is, let us take it as mass defect according to the Einstein mass. In starting, I talked about Einstein mass energy relation. That is E is equal to, right, that formula. The binding energy is expressed in joule, okay, as you know. So delta m is measured atomic mass unit, then binding energy is equal to delta mu. This formula will take. So I think you understand the energy that is required for binding proton and neutron is called as the binding energy, or opposite also we can say, right? Okay, in simple words I am explaining you that by what is the binding energy. In that binding energy, the sub is the binding energy per nucleon. Okay, the average energy required to release a nucleon from the nucleus is called as the binding energy per nucleon. So the energy that is required to release the any nucleon from that nucleus, from the nucleus to release the nucleon, the energy that is required, that is called as binding energy per nucleon. The formula is total binding energy by mass energy, that is equal to delta m into 931 by a into mev nucleon. After this, the fourth topic that we are going to learn in this nuclear physics chapter is binding energy curve. This is, I think it's not an important topic, but it is a small topic. Let us finish it off. There's nothing huge in this. So, how binding energy is graph? It is represented is binding energy per neutron and the total number of neutron, mass number A. So, the x-axis it is having binding energy per nucleon. Y-axis it is having y-axis it is having binding energy per neutron. X-axis it is having mass number A. Then so it is moving. So some nucleons with mass energy A greater than A is lesser than 20 have large binding energy per nucleon than their neutron. So it is not a important thing, I think. Next is the nuclear reaction. So this is also an important thing, that is the process by which the identity of nucleus is changed. It is a process in which the identity of nucleus is changed when it is bombarded by an energetic particle. When it contacted with an energetic particle, the identity of the nucleus will get changed. That is called as a nuclear reaction. Like take one thing, that is X parental nucleus plus incident particle A. It forms compound nucleus. Y compound nucleus plus P, that is product particle plus Q, energy is released. Where in this Q value or energy of nuclear reaction, Q value or energy of nuclear reaction, the energy of is absorbed or it is released during nuclear reaction. That energy it is known as Q value of nuclear reaction. The energy that is released during nuclear reaction, the energy we call it as Q value of nuclear reaction. The Q value is equal to mass of reactant minus mass of product C2 joules. That is mass of reactant minus mass of product into atomic mass unit. If Q is lesser than 0, then this reaction we call it as endothermic reaction, where the energy is absorbed in the reaction. The energy is absorbed in the reaction, then we call it as endothermic reaction. Q is greater than 0, then the reaction is exothermic, where energy is released in the reaction. In the reaction, the energy will be released. Then we call it as exothermic reaction. If the energy is absorbed in that reaction, then we call it as endothermic reaction. Now, law of conservation in nuclear reaction: conservation of mass number and charge number. In the following reaction, mass number let us take as A before the reaction, after the reaction. So before the reaction, the mass number is, in this given reaction, it is 4 plus 14 is equal to 18. After the reaction, the mass number, see, it is changed. 17 plus 1 is equal to 18, it will be changed. But charge number, it will also get changed, like so 2 plus 7 is equal to 9 was before reaction. After reaction, it became 8 plus 1 by 9. So mass number also it may change. Law of conservation in nuclear reaction will add. In this conservation of mass number and charge number, we have learned how it is there, how we can find. Now 4 plus 14. 14 is the helium value, that will be 18 in this given reaction. 2H to the power 4 plus 7 into the power 14, that reaction. 4 plus 14 is the helium, that is equal to 18. Here 17 plus 1 is equal to 1 is the oxygen. So okay, how what I think you understand. Conservation of momentum. Here linear momentum or angular momentum of a particle before the reaction, it is equal to the linear or angular momentum after the reaction. So The momentum or linear or angular momentum of the particle. What is the linear or angular momentum that is in of the particle before the reaction? It is equal to the linear or angular momentum of the particle after the reaction is takes place. And also conservation of energy. So total energy before reaction is equal to total energy after the reaction. Conservation of energy, the total of energy that is before the reaction, it is equal to the total energy that is after the reaction. Okay. Next is common nuclear reaction. That nuclear reaction led to artificial transmutation of nuclei. The nuclear reaction that led to artificial transmutation of nuclei is called as common nuclear reaction. Rutherford was the first scientist to carry out the artificial transmission of nitrogen to oxygen in the year 1919. His reaction only we have written here in the formula He plus N if O 17 plus H. So it is called as AP reaction also. The binary, sorry, that is common nuclear reaction is also called as AP reaction. Some other nuclear reactions are given like P comma N reaction. It is like this. So these are some of the reactions that they are given. So next is nuclear fission and fusion. So I think I will explain this in my next video. So okay friends, this much is enough in this video. I will explain the other topics in my next video in my next part. So I think till here you understand. So okay friends, see you in my next video with some other topics of this chapter, with continuation of this chapter. So if you thought, means if this video is got very much helpful for you, please give a like. Comment down if you need any help in studies, if you need study materials, question paper, or some any help in studies. Please comment down in any of my videos. I will definitely reply to you, and what help you need in the studies, I will definitely try to help you. And please share this video to your friends also. It may be helpful for them also. They will also learn some concept of this nuclear physics chapter. This is also an important concept. Means important chapter in this binary energy concept. Sorry, binding energy concept, binding energy per nucleon, and that many other concepts are there that may be asked for any competitive exam and also in your final exam that you are going to write, that is your 12th, any of the board it may be. Many questions may be asked from these chapters. So please share with your friends. It may be helpful for your friends also. So okay friends, see you in my next video with continuation of this nuclear physics chapter, and after that many other chapters explanation, some other videos also will be there for helping you. So okay friends, see you in my next video. Till then, take care, have a nice day. Bye my dear friends.